Today we are going to see how to build a bond graph model of this mechanical system that you see on the screen. And the question here is there a specific procedure that we can apply in such a way that we generate the bond graph model in an easy way and we don't make mistakes? So that's the idea here. So I am going to write down in here the what I would call steps to build a mechanical system model. And so we're gonna first step number one. Step number one is going to be to use a one junction to represent each distinct angular velocity, in this case angular velocity. Each distinct angular velocity. So the first thing we gotta do is to recognize what velocities we have, but also let me disappear from here so we have more space and you look at more interesting things than me. In here you have this let's look. You see, this is one angular velocity. Okay, this is another angular velocity here. So what I'm going to do is to use a one junction, and I'm going to draw it right on the graph right here. You see, and put a one junction. So this is omega 1 or theta 1 dot. Since you have it in there, I'll just write it like this. This would be omega 2, which is theta 2 dot, like that. And then I am going to say this is a velocity. This would be let's call it theta dot of the wall equals to 0. And just so that we have a good reference here, theta dot of the wall equals 0 here, but it is a velocity and is our reference. And then on the second step that I am going to do, step number 2, you're gonna say, okay, we are going to we say attach to the one junctions the elements that experience those velocities. Okay, very good. So maybe I move this a little. Oh no, here we go. We're fine. Right there. Okay. So in here on the right hand side, it's very obvious that we have this source of flow with velocity theta dot of the wall equals to 0. And I think I'm gonna need some space for my steps, so I'm gonna move them up a little bit. And then on the one junctions here we have this one that represents the I element, which is the mass, the inertia element in here, with value This would be j sub 2. We have over here the inertia element with value j sub 1. And so those are the inertias that we see. Now over here you have the in between these two you have a relative velocity, because it's got to be the velocity of this minus this, and in between this one too. So you have to think about that. In here you have this element see the difference between these two velocities. This one see the difference between this and the wall. This one see the difference between this and the wall also. So the next step is going to be step number 3. In here, over here, we're going to say use zero junctions to represent the velocity difference. Okay, and then I'm going to say, well, I'm going to do each step by step, one at a time. So that way we'll have this. So right here, I'm going to put the 0 right there. That signifies this velocity minus this one is going to be represented with this junction here would be theta sub 2 dot minus theta of the wall dot, like this. This other one on this side, on the right here, you're gonna have the 0 like this, and it will go this one, which would be theta 1 dot minus theta sub 2 dot, and in between right here on this we also have another 0 here. Because this is 0 velocity, it makes sense to draw it like this, see? And then this would be a 1, which would be theta sub 1 dot 1 dot minus theta of the wall. Okay, so those are the velocity differences. Our last step, our fourth step, is going to be to attach to the 0 junctions the elements that experience those velocity differences. Very good. So you see in here we are going to see the this is you have the C element in here, and you have this R element over here. This R with value whatever it is, p sub 2. This with value 1 over k sub 2. And then on this one too, is you see have the damping on the spring, so you have the C element, and then you have the R element. This with value b sub 1, and then this with value 1 over k sub 1. And then over here you see we also have these ones, and that is you have a C element with value 1 over k sub 0 like this, and this other one which would be an R element with value v sub 0. And lo and behold, what happens is that we have been able to draw the entire block, the entire bond graph. I am missing something here. Sorry, I missed. I should have put in here a source of flow with theta of the wall equals to 0. That I missed a little mistake in there, but I'm completing it now. So this bond graph model is good enough to put it into the CAMG software. And I drew the bond graph model on top of the actual system so that you can see the one-to-one correspondence of the graph to the model itself. Okay, it's very obvious that in here you could simplify things, and you can simplify things over here too, because you could say, okay, I know that when you have a bond like you see here, this one like this is equal to this, and the same thing when you have this would be like that, because the effort and the flows are the same on both sides of the junction, so it's not a problem. So in here I would do just one last step, which would be to assign the causal marks and number the bonds to have it complete. This last step, CAMG will do it for you. So if you put this model into CAMG, CAMG will go and number the bonds and put that we'll put the causal marks in here. I think that last step, although it's not necessary to putting this into CAMG, I am going to do it just for completeness to make sure that we have everything. And my objective has been here to show you how you can obtain the model very quickly. So for assigning the causal marks, I think there is also a procedure that I believe would be worth writing here. I'm going to say steps to assign the causal marks. Okay, and step number 1 is going to be assign the sources first. Assign the marks to the sources. Okay.
So there is no source of effort?
Efforts or flows. Say SE or SF. And C, you will say and see if the causality see if the causality fits assignment on the junctions, and see if the causality propagates. Then you will see in a moment what that means. Number 2 would be to assign the i's in integral form at the one junctions. Remember, the one junctions are the common velocity junctions. So I would go based on what I said. The first thing is I assign this. It's gotta be like this, right? Because it's a source of flow. This one is also like that. I go to the I in integral form. That makes this two like this, because the junction can take only one flow. You see, if the junction can take only one flow, then the others have to be this way. And you see here I put the mark to this one. Then this flow sets it for this one. The others have to be like this. like this, see? Okay, and we have to see if causality propagates. That means in here you see this flow, that makes this one like this, and now you have this and you have this, forces the zero to be like this because the zero needs a 1. So you assign the I is in integral form and at the 1 junctions and propagates the assignment, I would say, so that we complete our statement here. You could say and propagate the assignment you would say according to the what is required on each junction. So in here you have these two are flowing, and then this obviously will have to be like this. But the moment you do that, you force these two to be like this. And the same thing is true here. See, the flow in here makes these other two like that. And then in here you have the flows on this two, forces this to be like this. This flowing here forces this two to be like that. And you have basically finished. Okay, but in this particular case is because the causality propagated in here, but for completeness you say assign the zeros, the c's in integral form at the 0 junctions and propagate the causal marks assignment. I think this way you have to see at each step if it is complete. Now the model that we have in here is totally complete. Perhaps the last thing that we might want to do is do a little simplification over here and simplification over here, but I personally feel that it's not necessarily, and perhaps it's even more clear the way it is right now, because you clearly can see the reference points and also how the velocities and how the forces add in the whole system, and well, in this case the torques, because it is a rotational system. So that's how we generate the bond graph model for a mechanical system with systematic steps.